1 lab2. This lab is intended to compare the experimental and observed result of an object being thrown in a projectile parabolic motion and observing the effects of gravity and drag on said object. Physics principles involved are Newton's second law and gravity. Fnet is defined as the sum of forces of gravity near the Earth's surface and drag in this context. For the process, I wadded up a piece of paper and gently tossed it. System is the paper and surroundings is the hand, air, earth, and everything else. Initial conditions are listed below. Software used for analysis would be Tracker to break down the time intervals for observed data and calculations, and GlowScript to create a model for a predicted outcome using the initial position and velocity. In this experiment, I found that the observed path is somewhere between the model with just gravity and the model with gravity and drag. This suggests the presence of other unaccounted for forces. This is my data and the tracker video and our model picture. And these are the equations used. The first is the position update formula, and I plugged in our initial position and our average velocity found from the first two positions over our delta t. And the second formula is our velocity update formula, which, like stated before, Fnet is the sum of gravitational forces and drag forces. And noted below, F drag is negative the drag constant b times the magnitude of velocity squared in the velocity direction, but because it's negative, it's pointing away from the direction of velocity. This always means that drag will slow down the object. These are our results and the trajectory for each. And this is my GlowScript analysis. This code initializes the vector starting position and the initial velocity. It sets delta t to be 1/30th of a second because we were filming at 30 frames per second. And we set our initial time point to be t equals 0.233 seconds because this is when the paper left my hand. The bottom code sets Fnet to be the sum of gravity and drag, and also runs the position and velocity update formulas. This also shows calculating F drag in GlowScript. In this experiment, our object never reached terminal velocity. Velocity did equal 0 for an instant as the ball reached its peak, but the velocity never stayed constant. If the object was thrown from a higher position, it would be given time to reach terminal velocity. Thus, an experiment throwing a ball from a higher place like a rooftop would work. Terminal velocity would be noted as a horizontal line on this graph. And for an object to have zero net force, the velocity would not accelerate or decelerate. This would be the definition of terminal velocity. Possible errors and what ifs. Possible errors include additional forces unaccounted for, and for example, lift, which does seem to be the case. Rounding errors in calculations fed to accumulating errors that created some significant differences in our numbers. And I may not have chosen the proper center of mass for our tracker data. And our second what if the ball was thrown straight up with the same speed, what would have happened? I actually ran this through GlowScript, taking the magnitude of speed and only put magnitude of velocity and only put it in the y direction, and in GlowScript it never reached the ground. most likely because the ball's velocity in the x direction wouldn't affect the time to the ground, and adding that extra velocity to the y direction meant that its apex would be higher and take more time get coming back to the ground.